Hey everyone, so we're going to continue our discussion with projectiles, where this is actually going to be the beginning of two-dimensional motion. Now, so far the lessons we've talked about one-dimensional motion, where the object is either moving and accelerating in the same direction or in opposite directions, but for the most part it's within the same plane. So if it's moving in the vertical direction, it's also accelerating in the vertical direction. If it's moving horizontally, it's accelerating horizontally. This is called one-dimensional motion. We're actually going to go into two-dimensional motion. Now, some of the things that I talked about in the previous videos kind of fall in the realm of two-dimensional motion. In particular, the questions dealing with relative velocity, where you have a car or a boat going across a river, and the river is pulling it down in a perpendicular direction. So the boat's traveling west and the river's traveling south. And the question asks, what's the relative velocity? That's sort of two-dimensional motion, except there's a few aspects. First, we didn't really talk about the motion of that. We just kind of said, hey, what's the relative velocity? And we left it off at that, nothing much. It was really more of a study of how to combine vectors. But the other aspect is that in those cases, the velocities were constant. So it didn't really matter. If you had a scenario like that, the motion is now just going on an angle. That's it. There's nothing different. There's nothing really unique. You can almost ignore the fact that there's these two other motions and only look at the diagonal aspect. Now, what we're going to actually talk about is two-dimensional projectiles, where instead of throwing the object straight up into the air or straight down, now we're going to throw it off to the side. So it's going to end up having a velocity that is going horizontally and then an acceleration that's acting vertically. And this is going to give us very unique effects. So a few things to note. First, we actually have to pay attention and notice and make sure that we're aware that the velocity in the x direction is completely unaffected by acceleration in the y direction. This is a big thing in physics, is that acceleration really only affects velocity in that plane. It doesn't affect velocity horizontal to it, perpendicular to it. So we have to make sure that we're aware that when we start recording the information, that only some of the information gets grouped together. I mentioned before that typically when you're doing problems and you're writing down the information, one of the things that you kind of want to keep asking yourself is this positive or negative? Is it going up or down? Just to kind of keep track of the sign convention. Here, now we're going to have to add in another aspect, which is it in the x or in the y direction? Is this value going horizontal or is it acting vertically? Because depending on our answer, it's going to change how we approach the problems and what numbers can go into an equation. Now, one thing to notice is that if you look on the AP reference table, you'll see the equations given like this. V subscript x equals V naught x plus AX times T. Now, a few things to package. First, the reason they have these subscripts is to constantly remind you that if you're using, let's say, a horizontal velocity in for Vx, then you need to make sure that the initial velocity is also horizontal and the acceleration is also horizontal. Technically, I could actually rewrite this equation to be Vy equals V naught y plus AYT, because it means the exact same thing. Now I'm just flipping and saying that this equation only works in the vertical. This is very useful to do, but it's not something that you need to do. You can actually drop subscripts as long as you're being careful about what values go into the equation and making sure that only horizontal values go in at a time or only vertical. Now, another thing to unpackage from here that you may notice is that time doesn't have a subscript. That's because time's a scalar. It is unaffected by direction. It cares nothing about it. So it actually turns out that if we use these equations to solve for time using one of the dimensions, so we use the equations to find time in the x direction, well, that's the same as the y direction, because once it stops moving horizontally, it also logically stops moving vertically and vice versa. So the time values will end up being the same as long as the values that I'm using are consistent with each other. So that's the big thing to keep track of. The fact that now we have to separate x values with y values, and that time, because it's a scalar, does carry between the two aspects. Because we're going to do this, keeping track of the x and y's, one of the things that we're going to want to do is set up what we call an xy chart. So when you're dealing with horizontal projectiles, you're going to want to have something like this. So we have our chart. We have all the x values and all the y values based off of the scenario. Now, this is just a very common, type of information that they give us. So, like a lot of times they'll give us the height. Sometimes they'll give us the range or how far it lands, and a lot of times they'll give us that initial speed. So, I just want to show like how the chart gets filled out. So, if you recall, it doesn't really matter where you put the origin as long as you're being consistent with values. But I like to put my origin right here at the bottom left corner of the problem, because I like to try to imagine this as almost being like the first quadrant in a graph. So it even says it here, but we have the x direction, we have the y direction here, and I can think of this like all these values as being placed on a graph. So for example, since this is the origin, this would be considered 0, 0. Where I start up here, that would be 0 in the horizontal direction and a height h in the y direction. So if I start here, I'm going to say that my initial position in the x is 0, my initial position in the y is whatever height that object is. Same thing when it finally does land on the ground. It's not vertical anymore, so it's going to be 0 in the y direction, but it's moved some distance d in the x. So again, my final position here will be d in the x, 0 in the y. So again, it's just a easy notation. You can put this, the starting position, as origin. You would just have to make sure that the final position, the y, is a negative h. Same thing with the initial velocity. The initial velocity is acting exactly horizontal, hence horizontal projectile. That means that all the velocity has to be horizontal. None of it can be vertical. If there was any velocity vertical, that means that this would be tilted upwards at some angle, in which case it wouldn't be considered horizontal projectile, it would be considered angular projectile. And we'll do those later on. And then acceleration, the acceleration in the x direction is 0, and in the y direction it's negative 10 meters per second squared. Because again, we still have gravity pulling it downwards, but we no longer have an acceleration in the x direction. Nothing is affecting it horizontally. A few things to talk about. First, there's actually one other piece of information I do know based off of this. If we look here, the acceleration is 0. So that actually means that the final velocity in the x direction also is the same as the initial. So whatever they tell me about the initial velocity, I actually also know that's true for the final velocity. So it just gives me a little extra information. Now, in the x and y, it's actually useful to think of these almost as separate scenarios. So this object is moving horizontally. It turns out that, not horizontally, but in 2 dimensions in this horizontal parabola. Horizontally, though, because of this lack of acceleration, this ball is moving at a constant velocity. So just as we know about constant velocity, every second it's going to cover the same amount of distance. So if this is moving at 20 meters per second, every second it moved 20 meters, then another 20, then another, then another. And it turns out that if we add in gravity, it will still hit these horizontal milestones. So after 1 second, it will still reach 20 meters. After 2 seconds, it'll reach 40 meters. After 3 seconds, it'll reach 60 meters. And after 4 seconds, it'll reach 80 meters. So they line up horizontally. There's no difference between, in the horizontal aspect at least, there's no difference between a projectile affected by gravity and something moving at a constant velocity. Uh, I mentioned this before that the location that it ends up landing is usually called the range. Now, vertically, we actually have something else. If we look at these values, this actually looks a lot like one of our basic free fall problems where the ball is dropped from some initial height with no initial velocity and then it falls freely because of gravity. So if we actually treat the vertical aspect as just a simple free fall, we actually find the same thing. After 1 second, it falls a certain distance. The projectile would also fall that same vertical distance. After 2 seconds, it reaches the same. It falls the same amount as our projectile. Three, four, five, six, all of them will end up having the same vertical fall as the object dropped. Uh, and as I mentioned before, because of the fact that the moment the ball stops moving vertically, it also stops moving horizontally, time will end up being the same. It is important to note that these values, though, do have to represent each other. If you're using the y side, now this won't be a case here, but what I'm trying to say is that if for some reason the y values, you decide to stop here at some location, but the x values we're referring to it landing at this location, that's a conflict of information. So like in this case, the times wouldn't match. So you just need to make sure that the when you're doing that, carrying the time over, that the y values are referring to when it lands vertically, and x is where it lands horizontally. All right, so here's the first question. Pause video, work itself, go over a second. All right, so here I want to find the three motion graphs based off of what we know about the horizontal projectile. We're only doing the x direction because we can only make these graphs one direction at a time. And we're going to start off, we're going to make the claim of the, going to the right is positive. So the location of the cliff, wherever it's being shot off of, that is 0. And then anything to the right of the cliff, the direction it's moving, is positive. Now I like to start with acceleration. If we look back to that table, the acceleration in the horizontal direction was 0. So my graph is going to be 0. All right. If I go back to the table, I mentioned that the velocities were constant. Whatever it starts at, that's what it ends at in the horizontal direction. So my velocity should also be constant. And I should make it positive because, again, it's pointed in the positive x direction. And then based off of this, since this velocity is constant and positive, the graph for position should also be constant and positive. The slope for the graph should be constant and positive. So I should end up having a linear graph starting at 0 going upwards. So these are what the graphs will look like for the horizontal projectile in the x direction. Here's the next one. Pause the video, work itself. We'll go in a second. All right, so for this one, we're actually doing it for the y direction. So again, we look back to the chart. We can look at what's going on with the y values. Pretty much do the same thing. Identify what the initial values are. That's going to tell you where we start in our graphs. And then think about how the graph goes. Does it go constant? Is it a linear graph? Is it exponential? And the fact that only one of each can apply to these graphs. So if I look at acceleration in the y direction, it's negative 9.8, negative 10. And that negative 10 doesn't change. So my acceleration is constant in the negative direction. As I mentioned before, I like to start with acceleration because I only have three choices: constant positive, constant 0, constant negative. There are some times where you might see a graph where it's linear, but usually that's only meant for you to practice taking areas of that to find velocities. Nothing big. You won't actually have to do anything crazy with it though. Going back to the velocity, again, if I look at the table, I mentioned that the initial velocity in the y direction is 0. So my velocity should start 0, and then it's going to go in a certain direction. Now, because the acceleration is constant and negative, that tells me my slope should be constant and negative for velocity. So I should end up having a linear graph that is constant and negative. Now, my position graph, I have already done a linear graph and I've already done a constant graph. So for the position graph, I know I'm going to start with some initial position in the y direction, right? Because I'm starting at some initial height. And I know it's going to end up landing on the ground. So it's going to land at 0. So my graph is going to have to go connect to these 2 points. Since I already got the linear graph out of the way, this means I have to connect these using a curve. So part of the parabola. Which one would it go? Well, I'm going to look for one where the slope starts 0 and then goes negative. So it's got to start 0 and then go negative. So a perfect graph would look like this. This graph starts 0, and then as it goes, the slope goes negative towards 0. So this is what my y direction position graph are going to look like. Again, I do it the same way where I'm kind of paying attention to what the previous graph looked like. That describes the slope of the next graph. And then I also am taking advantage of the chart and paying attention to what was my initial values and what was the final values. All right. We're going to continue on doing some more practice questions in a bit. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.